fine. Okay, good. I'm going to switch off my video now, but yeah, nice to see everyone. Sorry if I didn't greet you back when you greeted me a moment ago. Anyway, so, and I hope you can all see the screen and the pointer. And right, so let's then move. Sorry, I'm having, let me.
Okay,
yeah, I'm struggling to move from one slide to the next. So if that doesn't work, I'm going to have to, should have tested that before.
Is it working now? No. Actually, have you shared the entire desktop or some specific screen of your computer?
Well, I was hoping that people would see the full screen at the moment.
Ah.
Not the case.
Yes, it is. I'm seeing the full screen.
Yeah, except that I'm trying to move to the next slide and it's not allowing me to do that for some reason. I wonder if it has to do with the pointer. Let me remove the pointer. I wonder if that will do it. Yeah, now it works. Okay, so it seems to have to do with the pointer. Can people see my mouse?
Yes.
Okay, now I'll use my mouse as a pointer. Okay, now good. Anyway, so as a title implies, I'm going to be looking at what one can maybe learn from the light curves of AGN. And thinks about developments in astronomy over the years. Imagine where we would be now if we didn't have variable stars. Much of what one learns from the behavior of stars, especially if one looks at how they vary, the periodicities, how fast they brighten and so on, is a basis for a lot of what we know in astronomy today. And but all that is only possible because people were able to identify certain patterns, whether it be the periods of oscillation or the rotational periods or whatever. So in order to actually exploit the fact that astronomical bodies are variable, one needs to also understand the patterns and then be able to derive some sort of a physics out of it. Now, with AGN, they've been known to be variable now for, since the 1960s and 1970s, essentially. So for many of them, we now have quite a long baseline, and we can look at how they behave over the years and so on. And of course, one of the first things that as soon as people realize that there's variability, they try to see is there some sort of periodicity in it? But to this day, one hasn't really been able to find very much, although I'm going to show you in a moment an attempt at doing just that. But given that we now have this baseline and we know that AGN do vary, some more than others, so we should now be at the point where we can hopefully in some way exploit the fact that these variations happen. I mean, how are they completely random? Or is there something underlying there which is driving it? And if so, how do we actually use that in some way or other? Okay, so I'm going to take you back to the picture that you almost won't find an AGN talk without it being shown at some point or other. But this is a unified model, and of course it was one of the great triumphs in this branch of research, where people were able to bring in this picture of the black hole surrounded by the accretion disk, and then a little bit further out, broadline clouds and the narrowline clouds and so on. All the observational evidence seemed to fit in very well with that. The fact that you had the broad lines visible in the spectrum, and the broadening being caused by dynamics, by the motion. And it would make sense that if those were in the vicinity of something like a supermassive black hole, and that this could cause the velocities which lead to the broadening of those lines, and that then further out you would have the narrow line and so on. And then also we had this, this torus being introduced. And the nice thing about this torus, apart from the fact that thanks to the work of people like Ian, we know that there is this dust in the vicinity of an AGN, which may play some sort of role in feeding it, in fact. But the nice thing about this was also that there was now a very nice geometrical explanation about why we get some types of AGN where you do see broad lines and other ones you don't see them, what we would call the type 1 and type 2 CFIDs. And yes, well, if we have this torus here, if you happen to be looking at from where my pointer is now here, then you would be able to see this inner region. And so you would see the broadline clouds. Whereas if you're looking from the side here, you wouldn't, because this would be hidden behind the torus. And about 20, 30 years ago, we had this very nice polarimetric observations where people were able to show that what looks like a normal CFID-2 galaxy in an optical spectrum, once you do the polarization, you actually do see broad lines simply because that would be reflected light or somewhere, and polarized light is often reflected. But what I'm going to show you later in this talk is that it's not quite as simple as that. So this nice picture we have here has potential, I wouldn't say problems, I think most of it is still right, but certainly we need to look at it, things a bit more carefully. For example, the one key question is, let's say we do have an AGN, which is a type 2 CFID, and then you later see it becoming a type 1. The only way this could happen within this picture if this whole torus moved or turned or so. But that, given how big it is and so on, and the dimension, would be something that you don't expect to happen in a very short time. It's something that you imagine would take the order of years or even centuries. So if this does happen, then there's a little bit of a problem with this particular picture. The other thing is where there's a lot of uncertainty is this whole question of the broadline region. Some people think that the broadline region are the outer edges of the accretion disk, and certainly some of the line profiles you get suggest that they are formed in rotating gas. On the other hand, you do get some AGN where you get the sense that they're not very close at all, and I'll show you some of those as well. So in fact, we're going to talk about something we refer to as an intermediate line region, which is somewhere around here. Okay, anyway, so let's then look at the history of variability in AGN. And here are some of the very earliest spectra where people realized that the spectrum that has been measured before is subject to quite a lot of variations. These are very well-known ones. This one was one of the original 6 in the list of CFID in 1942, and this one came soon after that as well, right? So the earlier spectrum, which in this case is this one and this one, a very clear type 1, nice broad H beta line over here, and then a few years later, in both cases, you see very little. This spectrum over here and this here would be what would be considered a typical type 2 CFID. So what we had already very early on really is examples of changing look type CFID. So anything which changes in a relatively short time from a broadline object to a narrowline object, we would refer to a changing look. So let's then look at the actual light curves. And as I said, and as the title implies, they look to be quasi-random and so on. They're fairly chaotic. A lot of the early work was done by people in the Soviet Union, and they just fairly systematically over many, many years observed some of the better known AGN at the time. And here's some examples, and you can see this is 1966 all the way to about 1978. Whenever they got the chance, they tried to get some sort of measurements. And all right, well, they shouldn't have maybe joined the dots with these lines, but you can see there seems to be very little pattern over here. This is more recent. This is from my PhD study in the late 1980s, early 90s. And here too, again, you do see clear changes. You see some sort of trends, but it's very difficult to see any kind of a pattern here. But let's then go a bit further. Look at, is there any sign of periodicity? If there's periodicity, for example, whenever you have black holes which are stellar rather than galactic, then you would immediately look at some sort of periodic signal. Okay, just before I get that, as people always like to see holiday pictures and so on, let me just introduce now my collaborators from China. And a couple of years ago, and I think many of the participants, people listening in, were there as well, we went to a place called Lijiang in southern China, where a group of people from here met a group of people from China, and the idea was that we should set up some sort of joint projects. And in our case, that happened. I discovered that Jianmin Wang and his people were interested in working with us. In particular, the reason being is that they had a very nicely set up program at the telescope in Lijiang, where they would every couple of days try and look at particular AGN, and then, well, take spectroscopic observations, and then do what's referred to as reverberation mapping. And they just had a slight problem with their site, and in that it's subject to monsoon rainfall. So for about 3 months of the year, the observatory almost shuts down. And those months happen to be about June to September. So, and that's normally a time when we get reasonably long nights at Sutherland. So I said, oh, well, how about if I join in during that particular period and try and help you and get a few data points for that. So that was followed up. They're based in Beijing. So I saw them immediately afterwards. And then just 2019, they actually organized a conference on reverberation mapping in Guilin, one of the nicest parts of China, which I was also able to attend. So thanks to the funders, which included people also from SAAO for this. Anyway, back to the science. So one of the things we discovered was that Yanrong Li was working on looking at possible periodicity in the long-term light curves of AGN. And he was looking at Arachelion 120, one of the very well-known and AGN, nice, bright one with lots of data. So, and I told him, well, actually, I've got quite a few data points which I haven't used yet. Why don't we throw it all together? And so I agreed. And then with that, this is what came out. Here is a light curve stretching, literally, this is from the 1920s. It said 1979 because this is when somebody went back to old plates to try and determine magnitudes. The data from here to here is much better. That's I think from the roughly 1975 onwards. And so what we see here is what might, and I don't want to say is, in fact, we're very careful, we said possible, what might be some sort of a 20-year period over here. Of course, and even the referee, and I think anybody who's worked in this kind of periodicity analysis will tell me, well, that means nothing yet. We want to see this being repeated another 20 years or so. Then we can maybe take it seriously. But at least it's interesting that there is this possibility here. I'm not sure if I believe much of what's over here. Also, there's some interesting things that right during the minimum, there seems to be a slight upsurge over here, if this really is a 20-year period. Anyway, so I thought that's nice, but yeah, we'll only know in 20, 30 years' time if there's really anything to that. Back to the reverberation mapping. And what we do there is that one takes a spectrum every couple of days, if possible, and then just compares the strengths of the continuum and various emission lines, mainly H-beta, but also others. So this is a light curve for the continuum stretching over 2 years, and this is a light curve for H-beta. And a couple of points here coming from SAAO. This is not so much Lijiang, it's also mainly from Cala Alto, where they have other collaborators. Right, but already here, if you look at this very carefully, if you look at where this peak is and where this peak is, you can see the H-beta peak is a few days later than the continuum peak. Similarly over here, also if we look at this minimum and so on. So this suggests that, and this is typically the kind of result one looks for in reverberation mapping, some sort of delay in the response of the emission lines to the continuum, because the continuum is it shows what's happening very close to the black hole, whereas the H beta would show you what's happening in the broad emission line region, so further away. So from that you can say something about, if you look at this picture over here, so if this is the ring in which the H beta is formed and the continuum is formed in the middle, then a sudden brightening at in the middle will take a little while to eventually affect and stimulate a response in the emission line region, and then it will go to the observer. So you can measure exactly how long that delay is, and that will tell you how far the emission line is being formed from the center. Something just to watch here is also following, because I'm going to use it in a moment. Let's say you're observing something over here. So you're observing an emission line which is created over here. Then what would happen is that you get the trigger, and then this takes a while to travel here, and then it will come back here to the observer. So effectively, it takes about twice the distance to go from here to here until you actually see it. Whereas if something happens over here, so the trigger happening here, exciting something over here, and then the light goes to the observer, you see no delay at all. So there is actually a difference between what you see happening at the back and the front. Right, so one particular galaxy that we looked at, is the one also I showed you the light curve a moment ago, is this one over here. And yeah, over 2 years, if you look at it as a whole, very similar spectrum, and that you can't really see much of a difference here. But where you do see, and this is a trick which has become quite popular in the discipline, to take the root mean squared spectrum. So you basically look at how much does any particular point along the line deviate from the mean. And what you see then is quite interesting, is that you see in case of the 2017 data, you see the Balmer lines, these are H, beta, gamma, delta, and so on, changing. And this is helium-2. This is helium-1 over here. Whereas if you look at the 2018 data, none of that seemed to be varying very much, except for the helium. The helium-2 is formed, because it's got a higher ionization energy and so on, it's formed much closer to the actual accretion disk and black hole than the others do. Anyway, so the fact that the 2 years are different, and also if one looks at the different lags found by different observers, quite a range over here. This suggests something else, that even though this reverberation mapping analysis has been so popular over the years, effectively, the assumption was always that what you see, it doesn't matter when you observe something, you can repeat the same kind of program many years later, and you'll still find exactly the same lags and so on. What's coming out now is that there's a suggestion that maybe things are not the same from year to year, and that there's some sort of change in behavior. This, of course, makes things, adds quite a lot of additional work, because it's already quite a lot of, to get all these data points, you normally can only do it with large international collaborations. So this makes it all a bit more difficult than people would hope for. But on the other hand, it tells us something about what's actually going on. These are just the correlation curves between the various emission lines and the continuum. And one can see also that the lag from 1 year to the others seem to be a little bit of a difference, certainly as far as some of the aspects are concerned. But we're looking at something where apparently the behavior in 1 year was not exactly what happened 1 season later. And we see this even more nicely over here. What's happening here, this is a profile, if you like, of the H beta line, and it's been subdivided into segments. This would be the blue end, and this would be the red end over here. And you can actually do, by splitting this line into these various channels, you can look at each channel individually and see what happens when you do a cross correlation with with the continuum and see what happens. And the interesting thing is here, in 2017, there was very little difference between the blue wing and the red wing. But in 2018, there was a difference. You'll find that the delay in the blue wing was much larger than the delay in the red wing. And what that seems to suggest is that there was an infall of material, whereas this year there was more rotation about the nucleus. If there's infall, then you expect if this has got a bigger time lag, it suggests it comes from further away, from the far side of the AGN. And if it's got a bigger time delay and it's blue shifted, it means it's coming towards you. In other words, we are seeing signs of infall, right? So over here, no particular infall. Over here, we have infall. I've also seen cases where people suspect there's outfall as well. So that might be linked to jets and so on. Anyway, back to the light curves. So I already showed this one earlier. So we had, again, it's a question of how do we interpret all this? It's a random kind of light curve. And just knowing that something is variable doesn't help us very much. We need to have some sort of a pattern that we can make a physical sense from it. And at that stage, I'd already been working on my PhD for many years, and I had a lot of data, and all I was seeing is random curves, and I didn't really know what am I actually going to do with this. I need some sort of a scientific finding to come out of that. And that's when I discovered what was a rather obscure paper. It was in a very minor journal, but what had happened was that this person over here had simply taken some of that data from the various Russian papers and had decided not to plot magnitude versus magnitude, because magnitudes is basically logarithmic, but had actually decided to convert the magnitudes into fluxes and found that there was what looked like a nice linear relationship between the two. I said, oh, okay, well, that's interesting. If we have a linear relationship, we can certainly do something with that. And one wasn't seeing that when one was plotting magnitudes, for example. So I decided, well, I have all this data. Let's see what happens when I do that. And lo and behold, this is what I got. And I think I've only had one Eureka moment in my entire career, and this was it. Now, suddenly I knew, well, I've got something, and this is what's probably going to get me my PhD in the end. And so it's question is, right, so we really seem to have this very strong linear alignment over here between the flux in one band and the flux in another band. So let's, by the way, the reason why I was getting better, a nicer linear fit than this other paper was simply, well, it's because the SAAO data is so good. With all the work on standard stars, the site was good for photometry and so on. So that's effectively makes the difference between my data and if you plot some of that earlier Russian data. Anyway, so how do we interpret this straight line? Well, what I was doing was aperture photometry. So you place an aperture, try and center the nucleus on it, and then just take a measurement. And bear in mind that what we are looking is not only the nucleus, even though in many cases the nucleus is very bright, but we're also looking at part of the galaxy around it. And these would then be two filters over here. And if I then look at this over time, as a nucleus gets brighter and fainter, we see it going up and down this particular straight line over here, but it will only do that if the colors of the nucleus stay constant. Now that was something that a lot of people were not very comfortable with, because they simply said that why should the colors stay constant? As far as they're concerned, the nucleus got bluer when it got brighter. Well, it only gets bluer because you are seeing the brighter inner part getting producing more light in relation to the galaxy background. But it seemed that other than that, the actual brightening was in such a way that that the colors always stayed the same. Something else is that what happens if you have a lot of dust in front of you? And so your nucleus won't be quite as blue anymore. You're going to lose some photons in all these bands. And the way what will then happen, you're still going to get the straight line, but the variation is going to be along a slightly different tangent. So you're going to have a less, in this case, less steep slope. So in a sense, the slope of this particular line and this line gives you an indication about how much obscuration there is in this particular nucleus. And this was something nice. I said, oh, well, we've got some way to actually determine how much light is being lost through absorption. What's more, you can also, using the same technique, okay, it's been applied by a couple of other people, and here is also a very nice result, a very straight line. And you can see the straight line doesn't go through the origin because the colors of the background galaxy are slightly different. But if you know what the colors of the background galaxy are, which is estimated here by this particular line over here, then you can, through the intersection over here, you can basically say that, okay, the host galaxy inside the aperture goes to here, and then from here to here, everything that happens here is what happens in the nucleus itself. So you can work out very nicely how bright the nucleus itself is, and from the slope you can determine what how much extinction there is, and from that you can tell very nicely how what the actual luminosity is. So that was a nice result. And also from the slope of those curves in the last diagram, so that tells you something about what the intrinsic colors are. And when I did that with all the sample that I had at the time, I got the following. And this to me suggested that, all right, well, we've got a concentration of points over here. These are also the bluest, right? Top in this particular diagram, top left means bluest. So it seemed to me that most AGN had almost exactly the same colors, and that when they didn't have those colors, it looked like there was some sort of reddening happening, which was fading or reddening both the U minus B and the B minus V color. And the interesting thing is that this here corresponds to the galactic vector. So that's what would happen when you plot stars. And in this case, we found a lot of points down here. And very nicely down here, this one, IC43229A, I'll talk a little bit more about that later. That seemed to be the most reddened of our nuclei. But note that this line does not exactly correspond to the galactic reddening vector. So we are looking at potentially a different kind of reddening law. Wouldn't be entirely surprising because we are talking about AGN after all, and I don't think it's nice being a molecule, an interstellar molecule in the vicinity of an AGN. I think it has all sorts of, it could have all sorts of effects. Anyway, let me now move on to some other cases where we found the very sudden changes in the properties of AGN. This is one, as I said, I've showed it earlier, it's one of the best known, quite close AGN, NGC 1566. It's quite a nice, sitting nicely in the south. And there's nothing particularly remarkable about it. We only know about it really because it's so close and bright. And this is what its spectrum looks like. Now, for people that have worked a lot with quasars and so on, this is actually very boring. There's very little going on here. So normally you wouldn't spend too much time on one of these. So let's see what then happened. Okay, and here again, people familiar with Sutherland will know that there's a Russian network of telescopes called MASTER set up there. And this Viktor Okniansky and some of his co-workers are running this MASTER telescope. And they are perpetually looking for interesting events happening in the sky and then try to follow up on that. And so they've also been looking at NGC 1566. And what happened here, this is roughly here, you can see the years 2017, 2019, and you'll see that very suddenly in 2018, we had an outburst over here. And whereas before that, very little activity, but then suddenly quite a dramatic outburst. So, right, so immediately told her, hey, can you try and have a look at this? You'd like to see what is going on here. And so we did that. Also, maybe look at what happened as the outburst then progressed. It then went down again. And in between, you had these rather interesting kind of brightenings occurring. But all right, so let's just see what happened with the spectrum. Here, this is a spectrum towards the middle of the outburst. And this is quite a change to what it normally looks like. Not only are the Balmer lines much, much stronger than they were before that, but we see a number of things which are totally invisible over here. Okay, helium-2, again, that's always associated with high ionization, but also a lot of this is Fe2, which we don't see here. And then also these coronal lines over here. Now, these you do find in some AGN, but we were slightly surprised to see them happening at this particular point. But all right, so this is the spectrum when this AGN was in a very bright phase. And we tracked it after that. We watched it go down. What I did look at is to see if there's anything that we can get from this particular light curve. And so I did try and plot the fluxes in B versus V and U versus V. Interesting enough, there was a little bit of a difference here between what was happening near the peak and what was happening at other phases, right? So over here, this is blue. This corresponds to these dots over here. These two correspond to what happens over here. And yeah, so there is this trend over here. There seemed to be sticking to this particular point here. Okay, anyway, let me move on. Right, just to, how do we interpret this particular thing and maybe a changing look events in particular? Given that we saw this in a fairly nearby, overall, not very luminous AGN. Right at the beginning, I also showed you that something similar happened in NGC 3516, also very close by. I'm wondering if maybe this is what's happening. If this was a very luminous object, perhaps there's this fairly constant stream of material, and if this slightly weakens or slightly strengthens, you don't see much of a difference. It just gets a little bit brighter, a little bit fainter. But maybe what we're dealing with here for NGC 1566 is something where, because overall the black hole is rather small, we just get it filling up in drips and drabs, literally. So we just get, whenever one of these blobs of material falls onto the black hole, we get this sudden eruption. And then afterwards, things are quiet again for several years. Anyway, it's just a theory at the moment. Okay, I've looked also to see if we can find similar changing look events. In fact, I had this as a master's project where we looked at a whole lot of spectra, roughly 68 AGN. And we found several cases where, indeed, if you compare a spectrum from about 20 years ago, just a more recent spectrum, quite a lot of changes in both ways. This one here, IC 1524, was a particularly nice one. I'm going to show some more results of it later. Also, it is relatively close. Okay, next thing I want to come to is a program that I've been exploring. Given that I stopped doing the photometry of the AGN for quite a long time, and I've now become aware of the capabilities of the Las Cumbres network, and was wondering if one can maybe continue doing it there. So I have started a project where I'm looking at, again, a series of about 60 AGN, and hoping to get some information. In particular, I'd be interested in just seeing them in a bright state and in a faint state, because from that you can determine how the nucleus changes. Now here, for example, is a result for IC 1524 I described earlier. That one I've been observing now for almost a year. So I've got every month or so I try and get a data point. Here indeed, you can also see this linear relationship between the flux in any particular band and the one from the other. From the slope, if it's a steep slope, it means very little reddening. If it's a flat slope, it means a lot of reddening. In this case, this amounts to a moderate reddening. So from that, we can tell then exactly how bright the nucleus is, how much it's being obscured, and so on. Okay, then I want to come to, I showed right at the beginning our Arachelian 120 and how there may or may not be a 20-year period. Now I want to show you a couple of AGN where, well, if there is a period, it's a very long one. It's probably of the order of 100 or more years. fact, I'm even wondering if some of these AGN just simply have one big burst and after that they never come up again. I think that's an unanswered question, and we might need to still wait many more years until we can look at that. But this is the whole question is, when we look at your typical galaxy, is this maybe one which at some stage in the past experienced a whole series of activities related to black holes and so on, but are now just in a very quiet state? Or is this something which is ongoing? Or is it something that happens, starts periodically? Okay, first one is IC198G24. When this was first observed, very nice AGN, very strong Balmer lines over here. And then if we look at it more recently, this was taken almost 3 years ago. Okay, you might say, well, it looks similar. It's actually not similar. Bear in mind that these lines over here don't change in luminosity. So over here, H beta is only about a fifth of the strength of what it was over here. If we look at more recent data, it seems to have gotten even fainter. Here's another one. Okay, now, and I put this in deliberately because this is one where I literally have seen the spectrum, but I don't, it's somewhere in the SAAO archives. I would strongly encourage SAAO to make all their past data somehow easily available on archives, because there's still a lot that can be done out of it. As far as I know, the spectrum was never published. I think it was taken by Kash Sekiguchi back in the early 1990s. But I did see it, and it had very strong H beta. And this is what it looked like about 2 years ago. Right, whatever H beta there was is almost gone. The little bit of broadening at H alpha, but this is very, very faint. So clearly it's now a very poor version of what it was when it was found to be very bright. For both of these, I've got assassin light curves. Now you might say, okay, this tells us that this is doing absolutely nothing at all, but bear in mind that we're also looking at the host galaxy background here. So it doesn't necessarily mean that this was completely flat, but whatever variations are in there, it comes from a very, very weak nucleus in a otherwise bright galaxy. Okay, this one was still doing some things. This over here is more or less where I took the spectrum that I showed you earlier. Now, towards the beginning of the year, it had faded quite a bit again. And when I actually plot the fluxes, this is quite dramatic over here. This is UGC 4248. This is how bright it was. Just remember, this is where I said I saw the spectrum. And because once I saw that spectrum, I put it on my observing list. So I got this very bright point over here. Observed it again 2 years later, it had gone down here. A year later, it was here. Here it was in 2000, here it was in 2002. And now observed earlier this year, it was right down here with a slightly different apertures. If we adjust for aperture, the point would end up roughly over here. Similarly here for the U band. So what we're seeing here is that over the last 30 years, this one has just progressively got fainter and fainter and fainter, and is now at the point where it's almost showing no activity whatsoever. A very similar pattern here for ESO 198G24. These data points are from the mid-1990s, it's early to mid-1990s. This is what it looks like now. Both cases very faint. So we're looking at a situation where once very bright AGN, which was just picked up in some of the earliest X-ray surveys, is now right down here. And the question is, will it ever come up, or has this now essentially seen its moment of glory and is now just going to become an ordinary galaxy? Okay, if I have, I'm going to just go through this very quickly. Just going to show you another object which is very interesting, Markarian 926. This one too, originally discovered in 1978, very bright in the 1980s, very nice, very broad lines too. That one too has over the years, so here it was at its brightest in about 1985, and then since then it's just gradually got fainter and fainter and fainter until now it's still a type 1, but really, I'll show you in a moment, but it's really not much else. Yeah, also some data from Ian here, who also followed this in the infrared. Okay, here's a spectrum from 1984. This is more or less when it was at its brightest phase ever. This is from 2004 from the Sloan survey. You can see a couple of things. While the width is still there, gradually it's just getting fainter and fainter, and it's showing a distinct asymmetry in its profile. This is what it looked like in 1999, right? So here too, you can see this odd profile. And then also, yeah, so it looks, a lot of these features actually look more like what we refer to as low ionization, narrow emission line region galaxy liner. And this is what it looked like in 2019. Notice that even some of these broad aspects have gone, right? Just to show you what the spectrum looked like in 1990, yeah, late 1980s, right? So it's now, it's difficult to, you almost can't call this is almost like a CFIT 1.9. And who knows, again, is this going to stay like this? Or is it suddenly going to get bright again? And if so, what is driving these particular processes? Right, next thing I want to come to is, I've talked about AGN which change a lot, but there's others which actually don't. And it'd be very interesting to find out why that is the case. I mean, why is it that there's some AGN which literally just don't seem to do much at all? And this comes from Beinisch-Paul's PhD work. So these are two spectra. Okay, they are roughly a year apart. Same over here. And the two of them are put on top of each other. Okay, right, you probably don't even notice that there's two spectra here. The one's in black, the other one's in yellow, right? Because they so match each other so closely. There's almost no difference between those. Then here's a different one again. Okay, this looks very noisy. This is not noise. This is all ion 2 emission. And you can see here that the red one, which is a later one, and this one, the earlier one, they fit very nicely on top of each other, right? So why is it that these ones just don't seem to be changing? In fact, it's not just over the sort of medium term, it's over the long term as well. David always likes this one. He was one of the people who discovered it, right? Back in roughly 1985, they found this. Okay, yes, very nice. Balmer lines, iron and so on, very nice spectrum. Okay, but at the time, nothing much else to report, except when you look at it over the years, there have been a lot of quite dramatic X-ray outbursts. And in fact, there was one such outburst back in 2019, where people immediately sent out a warning, oh, big things happening, look at this object. It just did amazing things in X-rays. Let's get a spectrum and see what's happened in the spectrum. Well, the odd thing is, and here we're comparing a SALT spectrum from 2019 and a spectrum I took 3 years earlier. Again, very little difference. You really struggle here to find anything substantial, which is different. I mean, these things is just something else, so don't worry too much about. But really, you can't see a profile change. You can't see one particular set of lines growing relative to the others. So why is it that some of these objects just don't seem to be changing that much at all? You know, I've put some of them, these objects, we refer to them in Beinisch's thesis as objects that have spectra similar to 1 Zwicky 1. It's like a prototype. So it's usually got very strong Fe2 lines and very weak forbidden lines. And so here I've just put on one here. There's actually, I think, 4 measurements I've managed to do. And again, within the error bars, there's actually no evidence that these changed much at all. And that's also true for some of the other objects of the class that I've got on my Los Cumbres program. Okay, then finally, I want to look at this question of obscuration and the reddening law. It seems a bit odd that one might be able to use data that one gets from the variations of AGN to actually study interstellar material. But I think we do have a couple of cases where this is indeed possible. This is also one of the oldest, well, known the longest AGN, IC439A. And if one just looks at an image of it in the sky, you can already see what's going on here. It's an edge-on galaxy, And this is a better image of it. You can even see the dust lanes, how they are affecting the light that's coming from the nucleus. But the nucleus itself is clearly a broadline Cepheid galaxy. And if we look at this more carefully, there is quite a lot of evidence that there's a lot of obscuration over here. Right? First of all, if you compare the strength of H alpha to H beta, which is also what Disney did, and Disney on that basis said that, oh, we've got an extinction of 4. Extinction of 4 means that the nucleus is really, 30, 40 times brighter than it actually looks to us, and that would make it the nearest quasar. So this was called the nearest quasar for a while. I'll show that that is not necessarily the case. Other signs, okay, you do get this interstellar line causing an absorption here, and just looking at this continuum, normally for a AGN, you'll find that it's much stronger in the blue. So there's clear signs that there's a lot of obscuration happening in this case, but that also makes it interesting, even though it makes it more difficult to do the observations. Right, so already before this, I'd managed to, just by looking at what when you plot the fluxes in one band versus the other, I came to the conclusion that it looked like the interstellar reddening in the vicinity of the IC43298 nucleus was different to what you get in the galaxy. As I mentioned, that shouldn't really be surprising, given that the interstellar matter that causes the reddening is subjected to a strong flow of X-rays and ultraviolet radiation and so on, which will probably affect the composition of interstellar material. So it's maybe not surprising that the interstellar reddening law would be a little bit different over here. Note, though, that it also seems to imply that the obscuration is not quite as big as it would, right? It's almost a magnitude in difference to what you would get with a normal reddening if you apply this other reddening law over here. And yes, in this case, we looked at, there seems to be this, most of these points seem to align rather with this red dotted line rather than what the reddening law suggests. Okay, so I got a couple of data points. Unfortunately, at this stage, it's only 2 with Los Cumbres. Anyway, the nice thing is at least it doesn't disagree with what we had earlier. But the idea is certainly that over the next 2 years or so, I'd like to collect a dozen or so points and see if I can manage to get this point tied down a lot better than it is on the basis of just simply 2 observations. But at least it's not somewhere completely different. So that's nice to see. So I'm hoping to get a couple of, to make this determine if there is such a line over here, because that would then tell us that there's a different reddening law and probably a slightly different dust composition in the vicinity of AGN. And just to finish off now, and this is another one, also quite a strongly reddened AGN. Right, if we measure H alpha to H beta ratio, it's about 10, so it's a clear sign. There's lots of obscuration over here. And I also managed to get a couple of observations with Los Cumbres. So initially it looked like that. This is certainly nothing I would normally present. But then yesterday, a new data point came in. And now this is certainly much better than what we had before. So with this, I can try and look at, well, what exactly is the slope here? And how does that compare to the unreddened slope? And if I plot that particular point, it comes right down here as well. So remember the IC4C29A was here. This is a slightly different one, 557 minus 383. So that one too seems to be down here. So both these two seem to be AGN, which have are reddened by about 0.8 to 0.1 in B minus V. And yeah, so I'm hoping to get a couple of more points. Anyway, with that, I've come to the end of what I wanted to say. Okay.
Thanks a lot. This really very nice journey, and we have a couple of questions and suggestions. So basically, I mean, you can read in the chat box. First is by Patricia. Like it's like why are the SAAO continuum observations from 1.9 meter for PG2130 plus 009 is so noisy, and where the other telescopes bigger? Yes.
Yes. Unfortunately, the way they do it at the other telescopes is that they have a long slit which they're able to rotate. So what they do is that in addition to the AGN, they rotate it in such a way that they have a neighboring star in the slit as well. And so they can directly, so if anything happens, they can directly, whatever happens to that will happen to the comparison star as well. Unfortunately, at SAAO, we can only have this east-west alignment of the slit, so we can't do that. So, that to me accounts for the noisiness. But yes, it is a bit of an issue, and it is, yeah, you're quite right. We're not quite as producing the sort of data that the other telescopes are.
Thanks, Hartmut.
But that's not quite correct. The spectrograph can be rotated. It's just it can't be rotated, you know, sort of dynamically in the middle of the night. You know, which is like, well, what's the point? You know, I've never understood why that was not properly implemented, because certainly there was a significant need to be able to rotate the slit to some angle.
Yes, quite right. Yeah. Yeah, so essentially we can't quite do it, but yeah.
So David, I mean, you have also asked a question about the same source. So about how many observations comprise the 2017-18 data set?
Yeah, I mean, you showed the mean spectra, Hartmut, of 2017 and 18, but I didn't quite understand how many separate spectra were there.
Okay, it would correspond to each one of the data points in that curve. So that's of the order of about 50.
Okay.
I would say, yeah.
Yeah, I mean, he's one of the suggestion is like, I suspect the archival data was lost in the big crash. That was for the same slide, or I think for some.
No, that was later when he was saying about that object where Kaz got some data, and Patricia, I noticed, said you might contact Kaz, but if you don't recall, there was a major crash, I've forgotten the year, where we lost essentially all of the SAAO archive.
Yeah, my suggestion was that, I know it's a big job, it would really require somebody to work on it full-time for quite a while, but I think it might be quite useful for SAAO to simply put whatever data they have and sort of make it available, and then just, I mean, they can set conditions on how to use it and so on. I just suspect there could be a lot of more papers coming out still with very little effort. That's just a suggestion.
But what I'm saying, Hartmut, is the data was on disks on our server, and then it was all lost, catastrophically lost for good. I know that there was then some attempts to retrieve stuff from DAT tapes, which IT people were doing for a while, but I have no idea what happened to that and what, if anything, was retrieved.
Right.
I think Patricia knows more about it from the archive of the infrared photometry.
Patricia want to ask something. I mean, let's hear from her. Okay, Patricia, please unlock. Yeah.
Thanks, Sunil. Hi, Hartmut. Going to the reddening question, there's a lot of evidence for very distinctly different reddening laws towards the center of our own galaxy and in the bulge. Quite a lot of work by Nishiyama some while ago, but also by other people. It would be interesting to compare your different reddening laws to other galactic centers. I must say I'm very dubious about measuring the reddening from the ratio of H alpha to H beta in such a complex environment, given that you have to assume certain levels of certain densities and so on. But I'm sure you know more about that than I do. But I do think it would be interesting to compare with the different reddening laws, particularly the work that's been done towards the center of our own galaxy.
Yes, that's a nice suggestion, because the only work I've compared it with are more studies of star formation regions where we know that the reddening law is slightly different, but I haven't looked at sort of going towards the galactic center. seeing if there's anything there. Yes, I think that would be quite good. I think the main problem with what I'm doing is really because, unfortunately, whenever you have an object that's highly reddened, it also means that you get very little blue light coming through. So the photon statistics are a bit of a problem here. And yeah, the Balmer lines, well, the main problem is we don't really know what the actual intrinsic ratio is.
No.
In AGN, it's almost certainly not 2.85 or whatever it's supposed to be. It's more like 3 to 3.5. But yeah, so it's only one indicator of what the actual reddening is. But I think we can safely say it's high in the object I showed you.
It's interesting that I sat looking at NGC 1566 for about 30 years, and it did bugger all during that time. So if I'd held on for another few years, I might have caught that outburst that you mentioned.
There were actually seemingly a couple earlier, but I think, in that paper with Okiniansky, we mentioned, I think, 2 instances, but I think those were even before you started observing them, where there was some signs that something seemed to have happened. So this, what we can say though is that one can use your data to show that we didn't seem to get anything over that period, unless it happened to coincide with the change of the seasons.
Yes.
Maybe we can have another discussion on 18070. This was asked by David again. Does it show photometric variability? And a 2016 paper by Pan et al. Showed that there was a possible X-ray QPO of the 1 hour.
Yes. I mean, that's a strange thing. And it's not only H0707-495, but other similar objects really do a lot in the X-rays over a very short time period. And what I think it might be happening there is that, and that could also somehow be linked with the fact that you don't really see any very broad lines. You see only lines which are moderately broadened. And that's also something that Beinisch is doing in his PhD. It looks like those are generated a little bit further out compared to where you normally find a broadline region. So whether there is no proper broadline region or what's happening, but it seems that when things happen there, you don't really see them very much in the spectrum. And even the continuum changes seem to be relatively small. There too, that's something I'm hoping will come out of all this Las Cumbres data, but that when you actually compare the range in variations, that it turns out to be less than some of the other objects.
Okay, great. Thank you. Any other questions? No, not those I can see. So maybe thanks a lot. This was really nice session. Thanks everyone for attending it. Yeah.
Okay.
Bye.
Thank you. Bye.
Thanks, Hartmut. Bye.
Right. Bye.
Thanks all.